by thanking the organizing committee for the invitation. So the talk today is for some basic idea for a Landau-Zener Stückelberg interferometry for the Majorana qubit. And this work is a collaboration with my former postdoc, and it is supported by WPI program and the grant in AIDS of GPSJ. Okay, if I have a time, I wish to discuss about the spin texture, so-called, in the Majorana quasi-particle wave functions trapped by a vortex. Okay, so everybody knows that actually the 2016 Nobel Prize in Physics was awarded to these three theoreticians for the discovery of topological phase transition and the topological phase of matter. Well, I just give a very small advertisement that we have a review article, quite long, 60-page, in this Advances in Physics the year before last year. So if you are interested, you can check this. This review article is for the quantum anomalous Hall effect and the topological aspect of the electronic wave functions. Okay, let me switch to the topic today. So I discuss about the looking for the Majorana fermion. Perhaps you know that actually this is a very peculiar fermionic elementary particle proposed just 80 years ago. And actually Majorana was looking for the real solution for this Dirac equation. And here we have this creation operator and the destroying operator. They are equivalent to each other. So the particle equal to the antiparticle. By the way, the electron is a complex solution to the Dirac equation. So they are related, but they are quite different. So first, as an elementary particle, this Majorana fermion, if it exists, it should be charge neutral. But it has not yet been confirmed for 80 years. But recently, people are discussing about the possibility to find some Majorana fermion-like thing in the topological superconductor. Of course, it is a quasi-particle, not an elementary particle. Why we need this superconductor to create this novel state? You know that superconductivity is actually a sea of Cooper pairs. So when an electron is traveling in the superconductor, sometimes it's scattered into a Cooper pair and an additional hole. And anyhow, the number of the Cooper pair is not fixed. So almost the electron is equivalent to a hole as listed here. But if you are considering a singlet pair, so that if the electron is spin up, then the hole should be spin down. So they are very different. Well, in order to have this condition, we need a superconductivity of chiral p wave, like this, or you need to the spin orbital coupling to suppress the spin degree of freedom. So this is the sort of request. And I'm going to show you one of the platform. Well, I just, salutation, I choose the formula, but I just tell you the meaning. So it is just nothing but a semiconductor, and we have a hopping of electron, and we can tune the gate and the chemical potential by this voltage, gate voltage. And we do have some spin orbital coupling, and we turn external magnetic field and to change the Zeeman energy, and we have superconductivity. So this is basic the system. And as you may know that if we have say this term, then we have a parabolic dispersion, and with this spin orbital coupling, actually this dispersion is split into two. So this spin, for example, up and spin down. Then you apply the magnetic field, you will open the gap across the gamma point. So basically, when we have the external magnetic field, and you can, then set the Fermi level in between this gap, and then if you have this S-wave superconductivity, say from the proximity effect, then you will open the topological, superconducting gap. So this state is topological because we don't have any spin degree of freedom anymore. So this is the story. But you need to have a sort of strong magnetic field to satisfy this condition in order to drive the system, here into the topological state. And so if we have, then we can solve the Borg-Liouville equations based on this Hamiltonian. Then we can have the spin null wave function This is for spin, this is for Hall. Then by combining them, we can define a so-called Majorana wave particle. So this is the definition. And I'm showing some results for this particular case, which I don't show the detailed parameters. But anyhow, at the 0 gate voltage, actually, we have 2 zero energy states. They are Majorana quasi-particle, okay? But when you tune this gate voltage away from the 0 value, okay, here, then you will find that there is energy splitting between this red and the blue, okay, dispersions. And I will tell you that, okay, so the wave function distribution for the, okay, 0 voltage, it is the red, and the blue, okay, curve is for finite voltage. You will see that they are almost the same, localized at the end of the nanowire. Okay, so it is about 100 sites for my model calculation. Then you will see that there is some overlapping between the wave function if the voltage is not non-zero. So it costs energy splitting at here. So this is the delta. But I only have 2 quasi-particle excitations within the superconducting gap. So I can steer. Also, I don't have the real, Majorana fermions, because this should be 0 energy in the superconducting state. But even though I have a finite energy state, but because, okay, I only have 2 excited states of quasi-particle, so I can use them to describe the system. And this is the theoretical idea, but last year, actually this idea was realized experimentally by the group of Charlie Marx in Denmark. So basically, they have this nanowire, this I believe indium antimony, I believe, and they have this green nanowire, and then they have the blue. This is for the aluminum, so it is superconducting of S wave, and then they applied the field along this nanowire. So basically, they can achieve the topological state, and they just measuring the charging energy, which is, we call this Coulomb-Brocket effect. You will see that actually this is the energy axis, and this is the strength of the magnetic field. When the field is very small, it is a conventional superconductivity. So we have this change of 2 electrons. Okay, we have so many possibilities for different number of pairs of Cooper pairs. But when you have a stronger magnetic field beyond some threshold, you will see that we have some new state corresponding to the odd number of electrons. This is nothing but the signature, experimental signature of topological superconductivity, and it can be casted into the Majorana fermions as the following. So this, I have the Majorana fermions at the left-hand side and the right-hand side. Then, like real numbers, by combination, in terms of this is imaginary unit, then I can create a so-called complex fermion, which is nothing but the electron, but it describes not exactly the electron, but the number of electrons. So it is the parity electron. So referring to the even number of electrons or odd number of electrons. So this is the eigenstate, and if do some calculation, I can tell you the I gamma L dot gamma R gives you the plus or minus, give 2 eigenvalues actually associated with this even and odd number of electrons. So this is the topological state. I'm going to use this, parity state to build a qubit. So this is the idea. So the setup is quite simple. So I have actually, this is nanowire already achieved by experiment. And then I have 2 of them, and I try to build a Josephson junction in between the 2 nanowires. So now I'm exploring this Josephson effect, basically. So the Hamiltonian I'm going to address is, so this is the energy. The energy actually depends on the coupling between the gamma 2 and the gamma 3 at the, the junction, or 2 sides of the junction. And here is the phase difference of superconductivity. Why the cosine function of half theta? It is meaning that the Majorana is playing the role. So if we only have the Cooper pair, we have cosine theta here, but I'm sorry. But because I'm playing the single quasi-particle, is the single electron-like excitation. So I have cosine half theta. So this is very important. And then I just inject the current from the left-hand side, and then I take the current from the right-hand side. And by increasing the current, then when the current is beyond the critical current at the Jefferson junction, you know that the phase difference between the two superconductors is evolving with time. I mean, to put it very simple, I can say, okay, it's a linear increase in the phase difference. This is nothing but the AC-Josephson relation. But this, okay, the voltage between these two superconductors also induce, as I already said, that a small interactions between these two, okay, say quasi-particles, the gamma 1 and gamma 2. Although at the very beginning, they are very small, vanishing. But here, because you have a voltage, so I have a, okay, small interaction in this section and that section. But they are very small as compared with the, say, Josephson effect of this Majorana fermion, and it is smaller than the voltage, okay, across here, and then it is smaller than the superconducting gap. So this is the regime I'm talking about. Okay, so as you see that we have totally 4 Majorana fermions. So basically, I have 4, okay, say, states of parity. But because current is always carried by this Cooper pair, because the system is in the superconducting state. So I have a totally, parity conserved. So I can concentrate one of the parity state, say, like even state. Okay. So this is, I reduce the, okay, say the 4x4 dimension into a 2x2 dimension matrix. So basically, this is the base is, okay, here, this is the even state and odd state described by this pair of Majorana, okay, fermions. And this is the qubit, is the combination between the even parity state and odd parity state. So this is the weight, okay, but they are complex numbers. Then what I had to do, I have to solve the time-dependent Schrödinger equation of this wave function. Then I gave this, okay, 2x2 matrix, so it's time evolution, and this is the energy of the, okay, even parity and odd parity state, respectively to each other. But I have a small interaction between these two states. It is due to the interaction here and there. So it's just the summation of these two delta. Okay, so then this is actually the spectrum as a function of the theta, the phase difference between the two nanowires. So away from, okay, certain values, you will see that you can well define the state as the even state or odd state, so like red and blue. But when they are close to each other, like at the pi phase difference, you will see that they are very close. And then this small delta, the interaction, okay, plays a very important role. So if I start from, okay, say the even state, then I drive the system by current injection. So the phase is evolving with time, then come to this point. So whether the system is staying this blue or, even state or changed to this, okay, say red state, is really depend. And this is the famous Landau-Zener transition. And I can tell you that the probability of remaining in the initial state, like in the blue state, is given by this formula. So when the delta is very large, you will see that the system will go like this. Okay, so this is the result. But it's not this only part of the story. So then I say, well, I have this even state started, then I drive the system to make the phase evolve with time. Then you will see that at this one cross, the system is going to a superposition of the even and the odd state. And this weight, actually changes with time. That is a accumulation of the phase, okay, quantum phase. Then you found along many, okay, say crossings, you have found that the system then will totally switched into the odd, okay, state. So this is called the Landau-Zener, Stückelberg oscillation. And then I tell you that there are two frequencies in my system. So the first process is nothing but the phase change of the superconducting phase difference. So this I just gave the m omega. But there is also a slow process. It is a variation of Majorana qubit state, as I'm drawing here. So by using the Foucault theorem, basically the system is periodic in time. So I can solve this problem by using this Foucault theory. And then I give actually analytically that another frequency, which is proportional to the small Majorana quasi-particle interactions delta, and it is also dependent on the Josephson coupling and the phase. How fast the phase of superconductivity changes with time. So this is the result. But you may see that because the delta zero, then the parity state is a good quantum number, so no change. So I need this delta. But you will see that why this superconducting frequency here does not change the physics very much. You will see that when this, say omega is very quick, meaning that the superconducting phase difference is sweeping very quickly. So at one cross-section, you will see the system is trying to stay in the system, the initial state. But then you have many because the frequency is large, so you have many times to cross the cross point, so that increases the probability. That's the reason it's a Bessel function, meaning that the frequency omega here does not affect this the rotation of the qubit so much. Okay, basically that's the physics. Then I performed some numerical calculation to show you more intuitively. So I start from say the even state, and then by driving the system by using this current, you will see that there is an oscillation in this Majorana qubit. Like this phi 0 is dropping and the phi 1 is increasing. And I can stop the system at a certain value so that the weight is stopping here so that we have a superposition between these two qubit state. And then after the interval of time, I can restart the system, and the system, the qubit will continue the rotation. So now I have already tell you, this cubic state is 0 and 1, so I can control the rotation in this, say, longitudinal direction. But then, so I can turn off this current injection, making the delta 0. Then, but this energy is still finite, so that actually the phase of psi 0 and the psi 1, they are still evolving. So meaning that I can also control the rotation in the latitude direction. So I can make a quite complete control on this Bloch sphere. So this is the idea. And also I can make this so the theory more detailed. I use this so-called resistive and capacitively shunted Josephson junction model to describe the system. Up to this moment, I assume that the phase difference is evolving with time linearly. So this is a strong current limit. But then I give a fixed, but finite current. Then there is, capacitive, and this is the ohmic channel. And this is the conventional Cooper-Pair channel. And this is the the Majorana channel. So depending on this, autopolarity or even polarity, the weight of them. And with the sign half of the theta. So this is the point of Majorana fermion. Well, I have two cases of small interaction, but anyhow, the point is that I should make the Markov number of my Josephson junction quite big in order to keep the coherence. So then this is the because now the current is fixed, but the voltage is is up to change with time, and this is the result for this qubit rotation. This is for voltage. You will see that there is quite an interesting pattern. And when I make this Fourier transformation, I get a spectrum like this one and 1 and 1/2. What is meaning of one unity means that this is the AC Josephson relation of conventional superconductivity. And this 1/2 is nothing but the rotation of Majorana. And sometimes I say that we have the 4 pi oscillation of Majorana quasi-particle. This is the Josephson effect of Majorana. And you will see, looking into the details, you found that splitting in this spectrum peak. This actually, the separation is proportional to the small interaction between the Majorana fermions in each of the two sections. So this is the story. And I believe I can still have several minutes for the second topic. So the second topic is the Majorana quasi-particle in the two-dimensional superconductivity state with a vortex. So the platform is as the following. So I have a conventional S-wave superconductor, and I have a 3-dimensional topological insulator where we have the strong spin orbital coupling. So then I have a vortex. And I'm going to convince you that when I have a vortex, then this system can trap 2 Majoranas, one at the top surface and other in the interface. So this is I'm going to show you. No, you cannot do me this. Okay. You look at that. Look at that. Let's look at that. Okay, I'm sorry. Okay, I make up. Okay, so this is the point. Then, okay, I just skip the details. The point is that, okay, there are two cases. The one case is the Fermi level is lying in between this bulk gap of the topological insulator. So in this case, we do, okay, have the Majoranas. Because at the interface or the top surface, we have this, okay, spin orbit coupled state. And then from the proximity effect, we do have the superconductivity. So this is the topological state. Okay, so that's the case. And then we do, okay, say BDG equation calculation. We found that actually, really, we have two, okay, states at, okay, zero energy. So, okay, I will skip that. The details. The point is that, okay, at the vortex of this, okay, say, topological superconducting state, now the orbital angular momentum and the spin, okay, angular momentum, they are not a good quantum number, but the summation of them is. So this is the total angular momentum, and this angular, okay, this is the orbital one. Orbital one gives you this, okay, say the lateral distribution of the wave function. So then I will tell you for spin-off electron, you will see this, okay, sort of spectrum as a function of the distance from the center of vortex. And this is the energy. So typically, this is the case. But for spin-down, you will see that it's quite similar, but a little bit shifted. But if you take the ratio between them, you will find a so-called checkerboard pattern in this okay, relative spin-resolved local density of state. And this actually, at the zero energy, this is the signature of Majorana quasi-particle state, and as a single quantum state. Okay, so I have to finish. Okay. So the take-home messages are Majorana quasi-particles are already found in the superconductor. Okay, and the Josephson effect help a lot in manipulating the Majorana quasi-particles in one dimension, and in two dimensions, and we do expect some unique spin texture, okay, of the Majorana quasi-particle trapped in the vortex. How's time? Thank you. Bye, thank you very much.
So thanks a lot, and thanks a lot for staying in time with. Okay, so the talk is open for questions or comments, please. Xiao Hu.